Hello Year 12 chemists, welcome to TP's Chemistry Cuts. The beginning of this clip is a general introduction to collision theory. We then go on to relate collision theory to a simple reaction mechanism.
Part one is collision theory. Now this section is all about how fast or slow a reaction goes. And this often comes as a bit of a surprise to students because when you do a reaction, particularly at middle school level, you add two things together and boom, they react. Well, the reality is that in the real world, most reactions don't just go boom like that. They take time. Some take a long time, some a short time, some intermediate. So they're all different. And having an understanding of why and being able to measure how quickly they're going is an important aspect of that. Okay? So, last year you went into how we do the measurements, so things like the volume of gas coming off a reaction that produces a gas, or a colour change as it deepens, you can measure as it's getting deeper. How many people here did level 1 chemistry? In the investigation, did you do the disappearing cross reaction? And that's a different way of doing it, in that the reaction produces a solid and the solution goes all cloudy. And so as the reaction proceeds, you can see through it less and less. And so what they did was to draw a cross on a piece of paper underneath the beaker with the reaction going on in it, and just measure the time it takes for the cross to disappear. And the faster the reaction, the slower the time. We don't need to go into the actual practicalities of it, okay? But we do need to understand what is going on, like we did last year, and look at the profile of a reaction. How does the rate change as the reaction goes on? Okay? So we'll start with that. Okay? Reacted that with hydrochloric acid, for example, then you get CaCO3, and I'm going to come to this in a minute, plus Now it's nice to start off with an equation because there are a number of things that we need to talk about in terms of expectations of chemical equations in level 2 chemistry. The first thing to say is we do not anymore deal with word equations. They have no value to us anymore. We need to know more specific stuff. They're all right for level 1 because we're more interested about the very basic chemistry that's going on. Now we're going to look at some more detail. It's an assumption that equations are always written out in as simple equations or formula equations, and you should be trying to balance them all the time. Okay? So if you struggle with balancing equations, you need to practice it. It's particularly important when we come to the quantitative chemistry internal assessment, but you should be up to speed with it. Okay? So that's the first thing. So you'll see I will always write out a balanced formula equation. And you'll notice now I'm starting to put in these things in brackets. How many people have not come across this before? Okay. For the benefit of you and for the benefit of those that have perhaps forgotten about this, what's really important to us when we're carrying out a reaction is we need to know more information than just a word or a simple equation can tell us. We need, in this instance, to know what the states of either the reactants or the products are, because one of them is actually very important. We need to know that this thing is actually giving off a gas. We also need to know, are we actually adding two solutions together? Are we adding a solid to a solution, or what? Because often you can do both, and they'll lead to very different types of reactions or different reaction rates. And so what this is telling us is that we're taking solid, so the little brackets with S tells you the state of it, okay, the physical state of it. So a little s in brackets tells us we're dealing with a solid here. So it's pretty straightforward. Okay. This is a little bit more challenging in that it's AQ. It's for aqueous, a Latin word which means in water. Okay, so it's a solution. So we're taking a solution in water. Okay, and we're adding a solid to it. That's really quite useful. And it's quite simple to do it on part of a line, so we're not having to write lots of stuff out. It's telling us that we're forming something that's in solution. So we don't need to look for that necessarily, or it might have a colour. This one doesn't, but if it's something else, it might have a colour. But it's also giving this off, which is a gas. Now, you know carbon dioxide is a gas, but other things you may not know as being a gas. So, for example, NO2 is something that's a gas, but you perhaps haven't come across that before. So it tells you something about the physical states of things, and that's quite important if you're actually going to carry out a reaction. In something like reaction rates and kinetics, speeds of reaction, then this is important. And so when we're dealing with collision theory, the whole section of this, and to perhaps a little lesser extent with all the other parts of this course, you will see that I will be putting in states because it gives us information that we need. Okay? Okay. So this is telling us that we're getting a gas in this reaction, and this is the thing we can use to monitor the rate of the reaction. So if we were to look at a typical graph of the total volume of this gas that's given out over time, okay? And any reaction, most reactions that are commonly encountered, which we can measure a reaction rate in some way, will give a profile that looks like this curve. Okay? Now, it's not important to put absolute values in here. Okay? What we're really concerned with is the shape of it, because we're going to interpret that now. So we're going to start off by interpreting what's going on in terms of the rate of that reaction as time goes by. Because that's what all the reactions that we'll deal with, that's what's happening to the rate. They all do the same thing, if not quite in terms of the same numbers. Okay? And then we're going to look at why they do that. Okay? So we'll tie the whole thing together using collision theory. So this is something we've done last year. Okay? And once we've done that, we can look at the factors that cause reaction rates to change. And then we'll move on to the next section. Right. So, how can we tell from that graph at any point the rate of a reaction? How do we work it out? What value do we need to work out that will tell us the rate of the reaction at any point? So if I wanted to know what the rate of reaction was here, how would I do it in terms of maths?
The amount of carbon dioxide made over time.
Yes, so from the actual graph itself, what's the value that we use? It's a mathematical thing from a graph. The gradient, okay, or the slope. Okay, so what does that tell us about the rate of reaction? The first thing we can say is that this is not a straight line, a linear graph, so the rate of reaction is changing as the reaction goes on. So we're not comparing two reactions here, we're just looking at the same reaction. So because this is a non-linear curve, it's telling us that the gradient is getting smaller and less steep as we're going along, which means that the reaction is in fact slowing down. So as time goes by, the slope is steepest at the beginning, which tells you that the reaction is fastest at the beginning. Then it's getting less steep, less steep, less steep, so that means it's slowing down, and eventually it's horizontal. And when it's horizontal, then the reaction stopped. Let's break this into three sections. So I'm going to put A here, B here, and C here. Okay? And we can then describe, and then we'll later explain what's going on. Okay? So you can see that the gradient of the line is very steep here. So that's telling you the reaction's going fast. So at the beginning of the reaction, that's when the reaction rate's at its fastest. Okay? What we can see is if we compare the gradient at A to where it is at B, it's clearly less steep. So that's telling you the reaction's going slower. Okay? So the reaction's actually slowing down. And then when we look at C, then we have a horizontal line. The reaction stopped. So there is no rate. Okay? The important thing is that the line is now horizontal. If it's not horizontal, the reaction hasn't finished. Okay? So we're looking at the beginning of the reaction. You've got the steepest slope, so the fastest rate. As time goes by, the line's becoming less steep, so the reaction's slowing down. And then at the end of the reaction, you've got a horizontal line, so the actual reaction stopped. So that's what all reactions do. They start off very quickly, they slow down, and then they stop. And the question we have to ask, or what we have to do, because you know already the answer, because you've already covered this, but we have to explain why that happens, because every reaction does it. Because collision theory will explain why this happens. Okay, so let's start off by saying what collision theory is. It's not some very complex, lengthy treatise. It's a very simple statement that covers a couple of sentences, or one sentence really. Okay, so what it tells us is for two particles to react, and it's common sense, they actually must come into contact with each other. Otherwise, they won't react. And that's important, so we need to state that. But that's not enough, because just about everything eventually will come into contact with each other, but not everything reacts. Okay? So there's an extra bit. And so the second part is that when they do come into contact, the collision that they do must be effective. So we're going to look at what we mean by that second part, the effective bit. Okay? So the important parts of that are the come into contact and the effective bit. Okay? So they've got to hit each other or collide, and the collision must be effective. Okay? We're going to look at what we mean by an effective collision. So we're going to look at a very simple reaction, the reaction between hydrogen gas, which is H2, and Cl2, chlorine gas. Okay, and that forms HCl. Which is in fact a gas. So hydrochloric acid in its pure form is a gas, hydrogen chloride. Okay, but at the moment this comes into contact with water, it reacts very vigorously with it and forms hydrochloric acid. Let's say there's no water present, and we're just reacting these two gases together in a vessel, a large vessel. If you go onto YouTube, you can see plenty of these reactions being done. Not allowed in schools, unfortunately. Too dangerous. Now, what I'm going to do is show you a very simple mechanism that pulls in a reaction, this reaction, using collision. So we're going to use collision theory to see what happens as these two simple molecules react together. Okay? So I'm going to use a very simplistic representation of each of those two molecules. So if we start with hydrogen, which is the smallest in the periodic table, so that's H2. And we've got chlorine, which I'm going to do in red, which is a larger molecule. So we've got two chlorine atoms joined together by a covalent bond. And these two collide together. So that's Cl2. So these two collide together. Okay? What has to happen first, okay, is when those two collide, those existing bonds must break. Okay? And so what I'll do is the equivalent of the existing bonds breaking, and we end up with individual atoms that are no longer bonded together. And the mind boggles as to what those actually look like. Okay? So and that's the really important thing. When those two reactive particles have collided, what's actually happened is some existing bonds break. In this case, all of them do, because there's just only two bonds. Okay? They're the only bonds possible, and they have to break, otherwise we wouldn't form any products. Okay? In some reactions, it might be you've got a more complicated molecule, only one part of it breaks a bond, and then a new bond forms. But in every reaction, this is what happens when a collision occurs, an effective collision, is that these existing bonds break. Once this has happened, you can now form a new set of bonds. So rather than reforming, and that sometimes does happen and no reaction occurs, but often this atom on its own will see this one on its own and it will form a new bond. And so you form new bonds and you get products. Okay? So we get so you get these new bonds forming. And it's at this point that we have to, for many, brush aside a misconception. Okay? We've got to understand what happens in terms of energy when bonds break. What does happen? Is it energy is given out, or is energy taken in? I'm glad you said it, because that's wrong. Okay? Whenever you break a bond, and there is no exception to this, if you break a bond, energy is always absorbed. So to break a bond, you've got to put energy into a system. It's not like a water pipe, a bond, and you break it and out comes all this energy. You're actually putting energy into break. Okay? And that's something you've got to remember. So just memorize that. So energy is absorbed. Okay? When new bonds form, energy is given out. Okay, so I'll put red for, it's danger, because you've got to put it in. Energy given out when it forms. Now this is so important, I'm going to put this as a separate thing. Okay. And this is so important, I'm going to put a box around it. And this is sort of like today's really big take-home message. It's really important you get this one right. Okay. So what I've tried to do is put up what we had on the board at the end of last lesson, because we were basically looking at a very simple idea of what a reaction mechanism would look like. What actually happens when a reaction occurs between two reactant particles. So we've said that they're going to collide with each other, because that's the first part of collision theory that states that for a reaction to occur, they've got to come into contact. So we're going to assume two particles collide with each other. And we're looking at a simple reaction between hydrogen gas and chlorine gas. And a hydrogen gas particle collides with a chlorine gas particle. And the first thing that happens is bonds break. And this is the crucial thing. When that happens, energy is absorbed. It's got to take energy. It's going to use energy to do that breaking of those bonds. It's not true at all, ever, that when you break a bond, energy is given out. Okay, there are no exceptions to this. It always takes energy to break bonds. You've got to put energy into the system. And the energy for that comes from the collision, the kinetic energy of the particles moving and hitting each other. That's what provides the energy. Yeah? Once the bonds are broken, then new bonds can form, and that actually produces energy. And when we come to look at thermochemistry later on in the year, we'll see how that actually maps out in terms of heats of reactions and so on. Okay? But for the moment, what we're really interested in is this first step, that we have to break bonds before a reaction will occur. And we've said we need to provide energy. And the energy that's provided, or you have to overcome, is what we call the activation energy. So for a reaction to occur, we've got to break bonds, and we have to have enough energy in the collision to do that, and that's called the activation energy. Okay? And if there is sufficient energy to overcome that activation energy, then the bonds break, and that's a successful or an effective collision. If there isn't enough energy, then the two particles will just bounce apart and no reaction occurs. So it's not an effective. And that's what we have to take on board, what an effective collision is. So I'll say it again, an effective collision is where the two particles collide with sufficient energy to break existing bonds. In other words, overcome the activation energy barrier, because it's like going over a barrier. So shall we write that down before we move on, okay? Really important part of that paragraph is the bit here at the end about what you've got are particles colliding with energy, but the only time you get a reaction occurring is when an effective collision occurs, and effective in this instance means they're colliding with enough energy to overcome that activation energy barrier. What we're going to do now is we're going to look at the two factors that determine how fast a reaction goes. And then we'll look at how we can adjust those two factors by changing things in the reaction, changing conditions in the reaction, so that the rate changes. Okay? Now there are two factors that determine how quickly or slowly a reaction goes. This is one of them. It's related to the effective collisions and ineffective collisions. And it's basically the percentage of collisions that are effective. The higher the percentage of collisions that are effective, or the higher the proportion of effective collisions, then the faster the reaction. It's fairly common sense. So if you've got 100 collisions and 80 of them are effective in one reaction, where in a different one you've got 100 collisions where 20 of them are effective, then the latter one's going to go a lot slower. Okay? So that's the first thing. The other thing that affects how quickly a reaction goes, or how slowly it goes, is the number of collisions that occur per unit of time. Okay, now that's a bit of a mouthful every time, so the best way to actually say it is the frequency of collisions, because it involves a time factor. Anything that's involving a rate involves a time factor. And here, the important thing is the frequency of collisions between reacting particles. So if you've got a reaction where you've got 100 particles colliding every second, and you compare that with the same reaction but you've got 40 collisions every second, it makes sense that the one where you've got more collisions per second occurring is going to go faster. Okay? So those are the two factors. Okay? The frequency of collisions between colliding particles, and secondly, the fraction of those collisions that are effective. So if you alter those two factors in any way, it will change the rate of reaction. Okay, so that's where we're at next. Okay. Now I can't emphasize enough that we're talking about a rate here, and a rate has a time factor in it. So it's really important when you're talking about this reaction rate and you're explaining it, that you don't just talk about the number of collisions. You must put in that time factor. So you must talk about the number of collisions per second or the frequency of collisions. It's really, really important. Okay, so I'm going to emphasize that by underlining that bit. Okay, and I'll write the obvious. The higher the frequency of collisions, the faster the reaction. Okay, the second thing, okay, is the fraction of collisions that are effective. The higher that fraction, the faster the reaction. Okay? The ones that have sufficient energy to overcome that activation energy break bonds so that new bonds can form. Only those collisions will produce or lead to a reaction. And so, secondly, and every time I mention an effective collision, I will say what I mean by it, and you should be doing that yourselves. Otherwise, it's just a memorized phrase that you have no idea of the meaning. Okay, so you should always, particularly when you're doing explanations, say what you mean. This year, the devil is in the detail. You are expected to put in all that detail. Last year, it's all about getting you up to higher and higher levels. Here, you've got to basically do the lot. Okay? And hopefully, both of those factors make sense. They're just common sense. Okay? Now, anything you do to a reaction system that alters either or both of those factors will change the rate of the reaction. Okay? So, if something you do causes the frequency of collisions to go down, just the frequency of collisions, then the reaction slows down. Some things we do will cause both factors to change. Okay? And you probably remember from last year. Okay, but we'll go through all the various things that will cause one of those two factors or both factors to change.